Hi, I'm Tycho Andersen. I am an engineer at Cisco working on Linux platforms, and I think my boss would be mad if I flew all the way here and I didn't tell you that we're hiring. So this sounds interesting. Come work with me. Today I'm going to talk to you about forwarding syscalls to userspace. And when I originally submitted this, this was still a work in progress, but now it has landed in the 5.0 RCs. So. Hooray. And when they do talks, they tell you to say something controversial at the beginning. So what I want to do is load kernel modules from inside containers. Good. I don't really want to do that because one of the things that you use containers for is you use them to run old user space that you don't necessarily really know what's in there, or maybe you work for this company that's been around for a really long time and has code older than you are, and so you have to get that working, and you don't really want to mess with that code, and it expects to be able to do all kinds of things. One of the things maybe is load kernel modules, and they don't realize that their kernel module is built against some super old kernel and you're using a really modern kernel. So what you really want to do is kind of intercept this call and just load the right one that you trust, that's built by somebody you trust, and kind of lie to the old user space and say, it worked. And they will get the functionality because the kernel API doesn't break and nothing insecure happened. Something else you might be interested in doing is mounting from inside containers. So there is a flag, I think it's called fs user ns mount or something. Particular file systems can enable being mounted from inside an unprivileged container, but in general this is not supported. And the code basically looks something like this. You can only do mounts as real root, which is reasonable because file systems have a lot of stuff like this. So this is, ext4 fill super. This is the part where they're parsing out some of the stuff that's on the disk, and there's like 1,000 lines of parsing code. And this is not necessarily bad. ext4 has lots of features. This is, if you look in this file, it's lots of endianness conversions. Like you can imagine sizes, things break in here, whatever. And in particular, this has always been only root can do this. So there's really been no security implications of this. We never assumed that some user could write some bad data to a block device and then exploit this code. But now all the container people have come along and said, well, we want to allow this. So this is, kind of sort of a problem, I guess you might say. But the reality is that people want to do this. And you can imagine there's a way to do it safely. So if you think about what happens when you're deploying a container on a cloud or something, you might write some image to the disk that's an ext4 image or whatever, and then your container tries to mount it. But if you know that block device has never been exposed to the container, you know that nobody has ever had an opportunity to write malicious data, and so only some legit image is there, and you might want to allow this. So what would that look like if we wanted to do that? Basically, the container would do some mount. We would go into the kernel, and there would be some magic in the kernel, and that would forward something to like a daemon or something listening on the host that would set an S to the container, do the mount, set everything up, and then basically lie to the mount command and say, sure, this all worked, everything's fine. So the question is, how do we implement that? It turns out there's a number of different ways to do this. The most obvious way is Ptrace. So you attach to every process in the container, and then you just step through the syscalls forever because you have to look at everything. And it turns out this is slow. You absolutely do not want to step through every system call that the container makes forever. But it is possible. So it turns out that people thought about this, and there's a seccomp implementation of this. And so there's a special, this is BPF assembly. You don't really have to, the part in red is the important part, where basically you can attach a seccomp filter, and you can attach to Ptrace, and you can just say Ptrace continue, but then when this seccomp filter triggers, you get a Ptrace event. And so that means you're still Ptrace attached to the process, but you don't have to do the whole step through every syscall. You only step through the ones that you're interested in. So this is obviously a vast improvement. But the question is, how do you debug something now that you're using this? So for example, you have a container, it's doing some stuff. You have this Ptrace attached thing that's supporting mount and whatever, but you can only Ptrace attach to one, only one person can Ptrace attach to a task at a time. So you use what's called the Fineman algorithm, which is, you just think about it really. There isn't really a good way to debug stuff without Ptrace. So one of the other motivations for this is that you want to allow debugging or people to figure out what's going on in containers. And actually, I didn't make a slide on this, but people actually use Ptrace in normal code execution. If you're familiar with Upstart a long time ago, or you might be if you're still running really old userspace, you Upstart Ptrace's services that it's starting in order to figure out when they do things like bind, so it can figure out when stuff's ready. This is sort of a precursor to the systemd socket activation stuff was that. So basically, if you're using this, then all of a sudden you can't run Upstart-based distros anymore, which may, again, not be a great thing. So, so we're almost there. But instead of seccomp trace, we want a new thing, which is seccomp user notif. I'm an engineer. I don't name things well. And so what does that look like? So when you're, the way this works is there's a file descriptor, and there's kind of a notification and a response. And the way you interact with it is there's some ioctl you can send or receive a request, do whatever you want to do, and then send a response. Things to note here. There's an ID. It turns out there's a time of check, time of use issue. So you might get this notification if the task dies and a new task spawns with the same PID. You don't want to take over that task and then start injecting all sorts of whatever stuff into its address space or its mount namespaces or whatever. So this ID is a sort of a cookie that you can use, and there's some stuff in the API that allows you to verify, is that task still alive? Is it the same task that started the system call? That way you can kind of avoid this time of check, time of use thing. And then seccomp notif response, you send the ID and then value, error, and flags. Why is there two responses? One is val and one is error. It turns out on some architectures, you return errors from a system call in a different register than you return successful options. And so the whole kernel has this infrastructure to handle this, and that's why this is exposed to user space as well, because you may be on an architecture where that's important. So how do we get one of these things? When you install a filter, you can say, give me a listener. So you can pass a program that has the special return code, and you can say, give me an FD back that is that I can do these ioctls or pull on. And then you can send message or similar to some server, or there's a million different ways to get this file descriptor out of here. One notable thing, if you saw earlier versions of this patch set, there used to be a Ptrace way to do this, where you could Ptrace attach to a task and then get one of these notification file descriptors. We ditched that, and the reason was that the LSM people, rightly so, you could potentially get access to a task with more privilege than you have by attaching to its filters, and they didn't like that. So we ditched that. It turns out there is a safe way to do it, but I thought it was kind of a hack, and we didn't really need this anyway, so I just dropped it. But potentially, there are some other use cases, so you don't have to do this whole send message dance if you don't want to. If you're interested in doing that, come talk to me. Question is, what does do stuff look like? How would you actually go about implementing that? So it turns out this is sort of slightly complex. so the struct seccomp data, which is the original, that's the thing previously in the kernel you would get exposed that has all of the register information and stuff. It doesn't include contents of memory because of the classic time of check, time of use, where there's two threads. One of them makes a system call. Seccomp validates this stuff. Then the other thread modifies the same memory area. It goes through the VFS or whatever and mounts the wrong thing. And yeah, you've exploited it. But we can sort of work around that with this, this new world here. What we do is we use this ID, and so we open a bunch of, we would open a resource, say like proc pid mem or something, so we can map the task's memory, and then check to make sure that we're still using the same system call request. And I'll have an example of that in a second. Again, you have to, when you're accessing memory, you have to do it through one of the existing interfaces, including Ptrace, but you don't have to be attached the whole time. So what that kind of looks like is, I guess this is an example of a policy, and you can see here we open proc pid memory, and then here's one of the special commands that you can check to see, is this ID still valid? Meaning, are we still in the same system call? I didn't just open the proc pid mem of some other process. So you can avoid the first time of check, time of use there. And then you read whatever memory you're interested in using, and then you avoid time of check, time of use number 2. And this one is the one that the lack of memory information in struct seccomp data is avoiding. So the problem is that these two threads one can change the memory content out from under the seccomp filter. But if we copy that into our address space before we apply a policy, then we can avoid that because the thread presumably can't write to our address space as well, the tracing daemon or whatever's address space. So there's a few implementation issues with this. The first big one is synchronization. It was hard. Seccomp has some stuff like this tsync thing where you can install filters in sibling threads, which makes things kind of complicated. The second one is this ID needs to be globally unique, and the way we solve that is basically by using lots of bits. So the ID increases every time, or it gets changed every time there's a new system call. And we just used a U64 so that it would wrap extremely infrequently, where that is like every 580 years or something. So, you know, that's just use lots of bits. This is one, there's I think a couple of threads on this, but the command and control protocol is using an ioctl instead of a write, and that's because write is for data and not for command and control stuff like this. And basically the problem is if you have a setuid binary that functions sort of like cat, and you have one of these file descriptors, you can cat commands into this thing and do bad stuff. So don't do that. For everyone in the future, I have replied to some other threads telling people to not do this, but just a public announcement. The next thing is to switch the file descriptor C groups. So SCM writes is, I guess actually, never mind. I should have dropped this because we don't do that anymore. There is no ptrace command. I mentioned this earlier because of LSMs wanting to do the privilege checking. It's possible but safe. So the FD passing stuff. So the deal here is there are certain system calls that return file descriptors. So things like open or socket or whatever. These system calls, if you want to emulate them through this framework, you need to have a way of returning a file descriptor, which basically means you need to have a way of injecting a file descriptor into another task. I tried a couple of different implementations of this. and there's some patches here that are fairly small, but kind of controversial because the VFS people don't like it when task A modifies task B's file descriptor table. However, there are a bunch of helpers that basically do exactly this, and this is just adding one more helper to that list. I don't actually need this for what we're doing, so I just kind of punted. But if you want to come along and use this for stuff like open or socket, you will presumably want something like this. There are implementations, they're fairly small. You know, check it out. So what's the status of this? It's alive. Please check it out. There's a bunch of stuff that I've fixed in the various RCs. There's some sample code here, which I'll go through in a second if there's no questions. And there's also some self-tests that test all kinds of things about it. And then I also have, just while I was working on this, I wrote a bunch of little utilities to do seccomp-based stuff, including there's cool things like you can trick the kernel into leaking restart sys into user space. And so there's a bunch of other interesting things there. So it's around, so now I can do a demo, but I feel like first, if there's any questions, maybe I can take that, otherwise I can keep yammering. Anyone? Yeah.
You were referencing the file descriptor parsing. I suspect the one thing you probably aren't able to support would be DUP2.
Right. So there's a couple of different issues, and basically the one helper that's missing is the one that you need in order to support DUP2. So I think there's install FD in somebody else's, and there's allocate FD in somebody else's FD table, but there's no replace FD in somebody else's table. And that's the one that we need to add in order to completely support everything that DUP2. But in those patches, it's like 10 lines to add this helper, and the actual seccomp code to do that is pretty small. It's really just, does somebody want to fight the battle of getting this into the VFS? But there are other helpers there, so it seems in theory like it should be possible. But if you wanted to do this without supporting DUP2, it would be possible to implement it today with what's already in the VFS. So yeah. Other questions? Anyone? Yeah. Yes.
So isn't that a case for just process-to-process communication with pipes or RPC or something?
Yeah, the problem is that the user space is old and expects to be able to do a system call. Some system call that you don't necessarily want to let it do, or you don't really want it to do that system call, you kind of want it to do.
Oh, we have LD preload for that, right?
Sorry?
We have LD preload. You can redirect the mount call to a library.
Assuming the binary is dynamically linked, right? There's Go and lots of other things. Really the only concrete interface is the syscall interface.
Well, what about a generic solution for redirecting any syscall?
That's what he has.
Or generic, isn't that what this is? Or maybe I don't understand.
I didn't understand. You are just redirecting the mount syscall, or?
No, well, so you can write a filter. So you can write a BPF filter that matches whatever syscall you want. So the examples I've given here are mount or make note, I think was the other one, or something. But it's just a seccomp filter with a special return code.
Okay, and what I didn't understand is the second process, which is meant for interception, is a certain process which is prepared for doing this interception in some way.
Yes.
So it's not an anonymous communication. So the partners are known to each other.
Yes.
Or at least one of them is known.
Yes. So the way people typically set up container runtimes today, there's some daemon that spawns the container, and often it has a watchdog that is actually the parent of the init. And so you can imagine either that watchdog or something else that's known to the container engine. The container engine is running as root on the host. It has all the power. So it's the one that can decide to do these operations or not based on some policy.
Okay, so just wondering, what about sockets? If you just have a listen call and a semantics and listen to something, and then you spawn a new handler in this other process space for it. So it's a known thing. It's just, well, I think this is the standard way Unix has worked for decades now. Or netlink interface or whatever. So I think there are more than 10 types of communication between user space and kernel space, at least.
And this is, you're saying this is another one? Or?
No, just wondering, because listen accept would be, for example, something which, and it handles the task of spawning subprocesses. Or at least it doesn't handle, but it doesn't interfere with it. It's a classical method.
Yeah, so I guess if I'm understanding your question, it's why are we implementing this versus just using accept and sockets and those?
For example, but there are several other methods. Okay.
Right, and the reason just goes back to I have a whole bunch of code that I don't, really want to make a bunch of changes to or whatever. We have this very concrete boundary that's the syscall boundary. Can we, manipulate this instead of changing this code to do some accept or, because then we have to go and make a bunch of changes to this code that already assumes it can do a mount or whatever. Other questions? Yeah.
Hi, does this work on syscalls that the kernel doesn't understand?
Right, so yes. In particular, there's no restrictions on the filter you write. So for example, you can invent your own syscalls with this. Because all you do is syscall number this, and then assuming the user space daemon is there to catch it and intercept it and sort of do the right thing, then yes.
So you could use it potentially to emulate other operating system syscall interfaces?
Yeah, there's a whole bunch of things that you could use this for that I have probably not thought of. We have a very specific use case. Again, and the functionality is not totally complete. For example, syscalls like listen, accept, these things that are returning file descriptors, you're going to need to, you'll have to do some work there. But the basics are there, at least for mount and some things that container runtimes want to do kind of right now or 5 years ago. Other questions? 1 minute. OK. If there's no more questions, the demo's not that exciting. The code's in the tree, so just go look there instead. Thank you.